Hello everyone, I am Mahesh DS working as Assistant Professor in Department of Electronics and Communication, SDM Institute of Technology, Ujjare. In today's session, we look into the overview and channel structure of LTE. Basically, LTE was introduced to develop a new technique that gives high-speed data as well as support broadband connectivity. LTE is a packet switch network from end to end and has no support of circuit switch services, which indicates that we can have also the VoLTE connectivity. What is VoLTE? Voice over LTE or call over internet is also supported by LTE. When a new technique is introduced, there should be a comparison between the new technique and the older technique. So we have the comparison of 3GPP with LTE, or in other words, we see what are the common things we find in LTE in comparison with the earlier versions of the cellular network. So let us see one by one. The first one is the network architecture. It is with respect to the physical architecture, how it is established. So LTE was designed to support packet switched traffic. Of course, that is why it is having high speed data rate. The previous versions we used circuit switched as well as packet switched. Packet switched for data transmission and circuit switched connections were used for the calls, and they were the standards made for the connectivity. LTE is different in the sense it is a clean slate design and it supports packet switching only so that data rate can be increased. So here the earlier versions of the network were taken into reference, but it is not followed as it is. LTE radio access network is and EUT run was designed to have the minimum number of interfaces. Thus, the ambiguity of making and breaking the connection is overcome over here. And here, the second point is the data rate and latency. You can see what is the data rate. As per the design, it is expected to be 100 Mbps and 50 Mbps respectively for downlink and uplink. But it is not definitely the same value, but it can reach up to 20 Mbps as per our practical experience is considered, and with the use of frequency division duplexing. So FDD is the mode which is used with the frequency of 20 megahertz. If the operating frequency is 20 megahertz, then you can expect 100 Mbps and 50 Mbps data rate respectively in the downlink as well as uplink. In the user plane, latency is very small, so we can see it is 5 milliseconds in a unloaded network. So what is latency? Again, it is a delay what we experience from the transmitter and receiver part. Now we have downlink and uplink as the terms used. So the latency is 5 milliseconds, and the latency states are designed according during the state transmission, that is when it is used, what it is used, and what is the type of data being transmitted or the command being transmitted. Then the performance requirement, we all know for LTE, we just expect a high speed internet connection. But as per the design is concerned, it should be increased in the spectrum efficiency and mobility as well as coverage. So here, this plays a very important role or vital role in spectrum efficiency, as 3G uses a different spectrum and 4G is totally different. That is why it's a clean slate design. And the mobility, it has got the very smooth handover, and coverage is very large. We look into the coverage area. So it covers larger areas compared to the previous versions of the network. Here the spectrum efficiency is done based on the high speed downlink packet data. So spectrum is perfectly used and data rate is increased. In the uplink, the average user data rate and the spectrum efficiency target is 2 or more times than the baseline what we used as a reference. And in the in the downlink, we can see 4 to or more times faster compared to the previous versions. In the mobility, when we move around, the minimum performance is expected for the lower terminal speed of 0 to 15 kilometers. This is expected to be a walking condition. In the mobility also, there is no glitch in the operation, as well as there is no hard handoff. So a soft handoff, or it is also called as smooth handoff, is possible with the data being considered, and the person or mobile phone user entity is moving at the speed of 15 kilometers per hour, and a minor degradation in the performance can be expected when the device is moving at 20 kilometers per hour. But it is expected, as per the design, it is expected to be able to sustain the connection from the terminal with a speed of 300 to 350 kilometers per hour, and this is significantly experiences a degradation in the system performance. Next is the coverage. To what extent, to what area it is using. For the cell coverage of around 5 kilometers is what we experience every time. For cell ranges up to 30 kilometers, a slight degradation in the user throughput is tolerated, and it can be experienced with a small adjustments in the performance. So significant degradation for spectrum efficiency is acceptable here when the range is up to 30 kilometers. But nominally, what we see is from 1 kilometer up to 5 kilometers is the normal range of the coverage. Then the radio resource management. When all the spectrum is available, it has to be shared between all the users, making sure that all the users are given with the equal priority, and also same level of services are experienced by all the users. It is called as quality of service. So from one end to the other end, quality of service has to be promised and it has to be maintained. So that is why radio resource management requirements cover various aspects such as end-to-end quality of service, efficient support for transmission of higher data layers, and support for the land sharing and balancing, and policy management, enforcement across different radio technologies. Now, these plays an important role in making or breaking of a call. Thus, it is called as radio resource management. Then we have the deployment scenarios and coexistence with 3G. As the title indicates, deployment scenarios can happen in two ways. One is a standalone, that is a new technique, a new connectivity brought into a particular geographical area, or it is integrated with the existing UTRAN or GRAN, that is the previous versions of the network. So in the standalone deployment scenario, where operator deploys LTE either with no previous network deployed in that particular area, or with no requirement for interworking with existing networks. If it is not combined with the previous network, or if it is a new network connectivity at that particular area, it is called a standalone deployment, and other one is integrated with the existing techniques, then it is called as the second type, integrated type. Next, we have the flexibility of spectrum and deployment. As we all know, spectrum plays a very, very important role, and it is not a free source. It is very, very expensive. To make sure that the service provider runs the system profitable, it has to be a flexible spectrum usage and deployment scenario. So here LTE was designed to be able to operable under a wide variety of spectrum scenarios, including the ability to coexist and share spectrum with the existing 3G techniques. This sentence says we can use the spectrum of 3G or previous versions for LTE, whereas services provided in different geographical regions often have different spectrums. As we all know, each cell uses a different set of frequencies. When we discussed about cellular structure and how frequency is shared among different cells, at that point we understood what are the different frequencies starting from 1, 2, 3, 4 naming, or A, B, C, D, E, F, depending on the cellular structure and the cluster size, the frequency of the carriers are varied. Which is why LTE is designed to have a scalable bandwidth from 1.4 megahertz to 20 megahertz. And also, in order to accommodate a flexible duplexing options, LTE was designed to operate under two conditions. One is frequency division duplexing, and other one is time division duplexing. Interoperability with 3G and 2G. When we make a call from LTE network to other networks, the call gets connected. How it is possible? So that is what the consideration made during the design. Multi-mode LTE terminals which support UTRAN and GRAN operations should be able to support measurements of and handover from to, and both 3GPP UTRAN and 3GPP GRAN systems. That is, all the operations what are happening in 3G or 2G network and LTE, that should match, and it should not make any difference in the operation. The terminal complexity and network performance should remain same for both, and it should be compatible. This is what the structure we feel once all the rules are followed. So network architecture is what we find over here. It contains UE, E node B, that is the previous BTS. Then we have the interfaces, mobility management entity. Then we have all other terminals or bridges, which is linking serving gateway networks, and GRAN, UTRAN, the previous versions of the network. This is the internet connectivity. PDN Gateway we find. PCRF is one more gateway which helps you to get connected to the network. So this is the architecture of the LTE. It is also called as end-to-end network architecture. You can and this slide shows the expansion of important terms to be remembered for writing the architecture. So EUT run and G run, policy and charging rules functions. So then we have the PDN gateway packet data network, which is related to the internet connectivity. Serving gateways we have SGSN is a serving GPRS support node. Then we have the MME mobility management entity, which makes your device more flexible in the movement. Then HSS home subscriber server, previously it was called as HLR home location register. And then we have the EPC evolved packet core, which links with the data. Here the explanation what it does. In the future topics also we have the detailed operation of each entity. In the architecture we'll just look into what we have in the architecture and what it basically does. So UE is the mobile terminal or a mobile entity which is used by the user. Then we have the E node B, which is a base station. Basically it is a base terminal transceiver section, BTS we call, which terminates the air interface protocol and is the first point of contact to the UE. This is the only network element which links with UE and connects through wireless connectivity. Then mobility management entity, it manages mobility of the 3GPP access such as gateway selection and tracking area list management. It makes the device more flexible in the movement. Then serving gateways, we have two types. It terminates the interface towards EUTRAN and routes the data packet EUTRAN and EPC. Then we have the PDN gateway. It is linked with the network connectivity and the data connectivity. It routes data packets between the EPC and the external PDN packet data network, and is the key node for policy enforcement and charging. Here we have the two types of interfaces which makes it possible. One is S1 interface. It is an interface that separates the EUTRAN and EPC. It is split into two parts, S1U and S1MME. Accordingly, in the structure what we have seen in the end-to-end architecture, the connectivity is marked. X2 interface, it is interface between the E node B's. It is between two E node B's and consists of two parts, X2C and X2U. One is the control plane interface and other one is the user plane interface. So that is all we have in this session. In next session, we'll look into some other topic. Thank you.